This week on Waterways, ocean acidification and sea level rise in the Tortugas. Coral reef ecosystems exist in a constant dance of construction and erosion. Reefs form when stony corals secrete skeletons of calcium carbonate, commonly known as limestone. As the corals build limestone to form reef substrate, many organisms simultaneously eat away at the limestone. Worms, sponges, fish. The corals are in a constant battle to maintain their construction, even facing destruction from hurricanes and tropical storm action. The constant building and eroding on the world's reefs have resulted in complex underwater cities because the building process has always outpaced the eroding. But that is changing. Research indicates that by the end of the century, coral reefs may erode faster than they can be built. This reversal toward a net loss in coral growth has been linked to changes in ocean chemistry that have been brought about by changes in the Earth's climate in recent times.
There's actually a recent study that came out a few years ago, and it showed that about a third of all the reefs surveyed in the Caribbean region were already showing signs of becoming net erosional.
What's actually really scary is we've done a lot of these calculations for the Florida Keys, and we find that presently a lot of these reefs are already in an erosive state. We can calculate that they're losing grams to kilograms of calcium carbonate, per meter squared per year, which is quite alarming if you think about it.
The Florida Keys coral reefs have existed in their current state for over 5,000 years. But there's been a change in the last 120 years, which marine scientists have recently focused their attention and is causing grave concern: ocean acidification. Acidic and basic describe two extreme properties in a chemical. Lemon juice, for example, is acidic, while milk is basic, or also called alkaline. A substance that is neither acidic nor basic is neutral. For example, pure water is neutral, but the waters in our oceans are slightly basic. Scientists have a neat way of placing aqueous solutions on a spectrum from acidic to basic. This is called the pH scale. The pH scale ranges from 0 to 14. A pH of 7 is neutral. A pH less than 7 is acidic. Lemon juice, for example, is 2.2 on the pH scale. A pH greater than 7 is basic. For millions of years, the water in our ocean has had a pH of about 8.1.
The pH of the world's oceans is currently about 8 to 8.1. And as the oceans absorb carbon dioxide, the pH actually declines. So we've seen a pH change of about 0.1 units over the past 100 or so years as the oceans have absorbed carbon dioxide.
Due to increasing levels of carbon dioxide or CO2 released into our atmosphere from burning fossil fuels like oil and coal, scientists are predicting changing weather patterns, more droughts and more floods, more frequent and more severe forest fires, rising sea levels, and an increased number and intensity of hurricanes and tornadoes. And this 0.1 in pH represents nearly a 30% increase in acidity. The higher concentrations of CO2 in our atmosphere is resulting in increased CO2 in our waters. And as CO2 gets higher in our waters, the pH lowers, indicating a more acidic habitat. The sky is falling, in this case, actually falling, into the ocean.
The geologic evidence suggests that the rate of change in oceanic pH that we're currently experiencing is occurring faster than anything the oceans have experienced within at least the past 55 to 300 million years. So this is a very concerning change in seawater chemistry conditions that organisms many of which have evolved since changes in pH have been seen on this order of magnitude.
What worries marine scientists is the effect ocean acidification has on creatures that use calcium carbonate for their skeleton or shell. Corals and mollusks such as oysters and clams have been shown to have reduced shell growth when subjected to oceans with high acidity.
And as pH declines, the rate at which they build these skeletons also declines. And this is concerning because coral reef ecosystems are actually dynamic systems whereby the rate that calcium carbonate is produced only slightly outpaces the rate at which it's eroded by physical processes like storms and also biological erosion by organisms such as urchins and sponges.
And the danger from acidification of ocean waters will not be limited to corals and mollusks. Some free-swimming zooplankton and marine algae lose their abilities to maintain healthy shells when exposed to an ocean with a lower pH. And that's not all.
Recent research has shown that even those organisms that don't build skeletons also seem to be impacted negatively by pH changes. For instance, fishes seem to have their echolocation disturbed as pH declines, which means that they might have a harder time finding suitable habitat in the future.
It is essential for each person to take steps to reduce the amount of carbon dioxide they are contributing to the skies and to our oceans. Instead of driving, carpool to work and conserve energy in other ways, such as buying energy-efficient light bulbs and appliances. American taxes are also responsible for supporting top-level scientists and implementing technology to figure out best management practices for our valuable resources.
To be able to gauge changes in the oceans, long-term monitoring is a very vital thing to do. There's two very long-term monitoring centers in Hawaii and Bermuda, and these two sites have actually been able to document ocean acidification over the past 20 years. Now, as we move into the future, we're setting up more monitoring stations throughout the world's oceans. For instance, we have set up an ocean acidification monitoring sentinel site at Chica Rocks in the Florida Keys.
Currently, right now, we have a MAP CO2 buoy at Chica Rocks in the Florida Keys. And this is a really exciting piece of instrumentation because it measures in real time the concentration of CO2 in the water as well as the CO2 in the air. It also, at the same time, measures things like temperature and pH. And so with this data, we're able to see exactly what's going on in the chemistry on a reef today. We can see fluctuations from day to night, we can see seasonal cycles, and we can see over long periods of time that CO2 is likely increasing.
The Ocean Acidification Monitoring Buoy at Chica Rocks was built by NOAA's Pacific Marine Environmental Laboratory in Seattle, Washington. MAP-CO2 stands for Moored Autonomous Partial Pressure Carbon Dioxide. The data collected by the MAP-CO2 buoy relays data back via satellite internet to NOAA's Atlantic Oceanographic and Meteorological Laboratory located near Miami.
Today we're going to be going to Chica Buoy, the Chica Buoy that we have that measures, it's a MAP CO2 buoy, so what that means is it measures PCO2 in the water, it also measures salinity and temperature and pH, and so what we're doing is we're going to go out there, take some water samples. I'm actually going to clean one of the instruments, and then what we do is we use those water samples to calibrate and validate the buoy data.
There were multiple reasons Chica Rocks was chosen for this buoy location. For one, Chica Rocks is a patch reef located in shallow water just offshore of the Upper Keys. This reef is one of the few sites in the Florida Keys that has shown a very high resilience over the past 30 years, when coral cover on reefs throughout the Caribbean declined.
Coral cover on the offshore reef tract is now about 5% or less, whereas coral cover at Chica Rocks is about 30 to 40%. So we're interested in understanding what is really creating that perfect recipe of resilience for this coral reef site.
Every 2 weeks, someone from NOAA's Meteorological Laboratory team visits the Chico Rocks buoy to collect water samples to ensure that the buoy is correctly calibrated. These samples are then brought back to the lab.
To do this, we simply fill up a bottle of water with that's CO2 impermeable, so that we know that no CO2 can go in and out of the container. We also poison it so that we know that there's nothing photosynthesizing and nothing respiring in that clean water. Then we can take that water into our laboratory. We take it into some machines that titrate it and run it through different types of instrumentation, and we're able to calculate we're able to directly measure a couple things such as total alkalinity, dissolved inorganic carbon, and we can use these things to calculate a whole bunch of different parameters which help us and inform us how carbonate chemistry and ocean acidification is progressing.
Since the time the MAP CO2 buoy has been deployed, Drs. Manzello and Enox have made some observations. Seasonal cycles in ocean chemistry were detected, and changes in ocean chemistry took place when a tropical storm came through. Data gathering on the nature of ocean acidification is important to our leaders in Tallahassee and Washington, who are tasked with creating laws to combat climate change. But just as importantly, it helps resource managers make decisions about how to best protect the natural environment and cultural resources under their protection. Ocean acidification, brought about by global climate change, is not the only impact that concerns resource managers. Warmer atmospheric temperatures are causing the polar ice caps to melt, and that is contributing to sea level rise. In June 2014, Dr. Erik Stebanow from the National Park Service led a team in placing a tidal gauge under the docks at Dry Tortugas National Park, located 70 miles west of Key West. The park includes a cluster of 7 tropical islands and Fort Jefferson, the largest all-masonry fort built in the United States.
So the Dry Tortugas Sea Level Monitoring Station is going to help us out in both knowing the local conditions, relative sea level rise rates right here at the fort. So when we're concerned about what to do with restoration and prepare and stabilization of the fort over time, we'll have that local information of what's going on. In addition to that, we're going to pick up local information, events related to storms and hurricanes that pass through this area in the tropics. So we get to see, we get storm surge, a very high rise of water level when these storms pass overboard.
Sea level rise has the potential to affect the cultural resources within Dry Tortugas National Park in a number of ways. First, Dry Tortugas National Park was created to protect and preserve Fort Jefferson behind me, as well as the collection of shipwreck sites within the national park boundaries. There are approximately 200 documented shipwreck sites within Dry Tortugas National Park. Sea level rise obviously is going to affect the level at which the sea interacts with the scarp or the outer wall of the fort, and if it rises significantly, it will eventually flood the interior of the fort. Dry Tortugas National Park has a variety of natural resources. We have submerged coral reefs, tropical reef system that is the 3rd largest in the world. We also have a collection of nesting seabirds. We have 2 different seabird colonies, the tern colony that's directly opposite us right now, and we also have a frigate bird colony that nests here. We also have sea turtles that nest on many of the beaches on the islands throughout the park.
The Dry Tortugas Islands are very low in elevation. The smaller Bush Key provides critical nesting habitat for bird species. Between February and September, as many as 100,000 sooty terns may gather on the island to nest. Sea level rise could have profound effects on nesting colonies of birds, marine turtles, and other organisms that depend on low-lying islands. Computer modeling has provided estimates that global sea level will rise between 8 to 80 inches worldwide by 2100. The exact amount depends on the rate of melting ice caps and how much the ocean temperature will rise. But this is the average rise worldwide. Actual sea level rise varies from location to location.
Sea level rise is a relative effect. Anywhere we consider sea level rise, what we're really concerned is what they call relative sea level rise, and that's the rate that the water is rising compared to the rate that the land is moving. Generally speaking, we don't think of the land as being mobile, but the land is. It is either subsiding or building up in different areas, and so the relative rate at each location will be slightly different. Global sea level rise or global sea level change is an average of sea levels around the world. Sea level rise rates that we measure in a relative sense is exactly what's happening to the sea level relative to that location. So that's what this gauge is going to do for us here at Dry Tortugas.
For over 100 years, NOAA has maintained a monitoring station in Key West Harbor, recording sea levels and storm surge. NOAA makes this data available to researchers from all different fields of expertise. And while these long-term data sets have been indispensable to scientists watching the environmental changes in our world, the information has been specific to Key West, waters 70 miles away from the Dry Tortugas.
The leaders in water level management understanding for our nation is the work done by NOAA, and they have a network of tide gauges around the nation. Some of the gaps in their network are in parks that the National Park Service, of course, manages. So we're installing gauges to provide that information at the National Park Service at each individual unit so that they'll have the water level information that they need, but also to complete the NOAA network of tidal gauges around the nation.
Storm surge events observed in Key West are also not the same as would be observed in the Dry Tortugas. By having a localized tide gauge, National Park staff can capture information on nearby storm events in addition to sea level rise. And knowing more about storm surge patterns could help preserve the park.
The Dry Tortugas tide gauge is going to provide sea level information. It's going to allow us to better decide how to do the restoration and stabilization of the fort. It's also going to provide us information about the natural resources here. Many of these low-lying islands that have to deal with this sea level rise issue. Some of these islands are maybe a foot above sea level at their highest, and we're watching these type of projections of sea level rise coming our way. We'll be monitoring here and knowing what's coming up with that. So both for the cultural resources and the natural resources in the park.
Mitigation of future damages as a result of climate change is very difficult. Probably the best thing that we can plan for is how are we going to manage this park at different levels of sea level rise and different intensities of climate change. What are we going to do? What is the park going to look like 50 or 100 years from now? And that's what we're actively working on right now, is planning for that type of change to occur. And we're calling that climate change scenario planning.
Climate change scenario planning. We know it's happening, but we don't know the severity of the change. So we plan for a variety of scenarios from best case to worst case. It is the job of scientists like Drs. Eric Stebanow, Derek Manzello, and Ian Enox to provide information and analysis that will protect our cherished cultural and ecological resources. Scientists are using other technologies to help measure coral growth, including instruments that measure the density of coral calcium carbonate skeletons.
We've actually started using a MicroCat Scanner, which is a piece of instrumentation that's very similar to what you would see at your doctor's office, where you go in, get a CAT scan of your bones and know the density of your bones and know different things about your body. We're able to actually CAT scan corals, but we can do it down to 7 microns, which is tiny, tiny, tiny. So we can look at the density changes, the changes in growth at this really, really small scale.
Corals, like trees, have density bands. By examining a tree's rings, a trained observer can determine the age of the tree. Similarly, when a coral's bands are examined, information about age and rate of growth can be ascertained.
So for the core sampling, what we're doing is we're going to go out and with the dead corals. So we're looking for a specific massive coral. So that's the mounding coral. And what we do is we go out and we take a core sample of it. It'll be about a foot, so 30 centimeters, so about a foot. And what we use that for is it's basically fresh carbonate. So it's just plain rock.
take that core back to our laboratory and we cut it down and we put it in our CAT scanner. And our CAT scanner will show us all of the changes in density. You can see through the skeleton, so we can know how it's growing, in what direction, how much distance it's accumulated in each year. So distance apart of the bands, also the density between the bands. And then we can really know how that changes in coral growth, how that coral growth is changing from year to year.
To accurately measure coral growth, scientists have begun using a 3D scanner similar to the machines utilized by engineers and for special effects in movies. This scanner measures the coral skeleton in 3 dimensions, which provides a more accurate measurement of coral size and therefore the rate of growth.
We're able to quite quickly scan a coral and measure its three-dimensional surface. So if you think about a coral has all of these branches or all of these bumps and grooves on it, to actually determine how much that's growing, how much that surface area is changing, how much that volume is changing, because these are so structurally complex objects, we actually need to measure them in 3 dimensions. And so we have a 3D scanner that we're able to quickly monitor the surface area and volume.
By looking at the records in coral growth, scientists hope to understand how actual reef ecosystems will change with ocean acidification, and better understand the relationship between acidification and the annual rates of growth in corals. Scientists are also interested in how boring worms and other eroders that break coral down will be affected by increasing ocean acidity.
And with this, we can actually calculate the net amount of skeleton that's put down per area per year in these different conditions, because we simply add the amount that's being put down by corals and subtract out what's being taken away by eroders. If we have a system which is net additive, we know that there's active growth occurring. If we have a system that's net erosive, we know that that habitat is trending towards loss of structure.
Why are reefs teeming with life, whereas sandy sea bottoms seem desolate? It's the structure. Why do fish and invertebrates colonize a newly sunk artificial reef? Structure. But what happens if there is no structure?
A lot of the evidence right now is quite alarming and quite depressing. And as somebody that studies this every day, it's really difficult to maintain sometimes maintain a positive attitude when all the evidence is really quite depressing. I think it's important that we identify means by which we can reduce our impact on reefs, but also hopefully identify ways that we can mitigate or to correct what we've already done.
25% of the species that live in the oceans live on coral reefs, and more than 1 billion people worldwide rely on food from the ocean as their primary source of protein. If the reefs are irreparably damaged, so is the quality of life on Earth for millions of people.
So I think the most important thing right now is knowledge. Understanding what is actually happening in our world's environment is crucial, because there's so much misinformation out there. And the bottom line is, facts are facts.
The fact is that our oceans are becoming more acidic. What is known to a lesser degree is what this will exactly mean for the marine species like oysters and corals in the next 100 years.
So it's really imperative that we really get our facts straight and send the right message, and that people really understand what's going on with the world's oceans. Because once the general population understands that the ocean pH is declining, and this could have dramatic ramifications for coral reefs. It could slow oyster production on the east and west coasts, which has direct ramifications for local economies. I think people will be concerned and really want to enact policy change to really curb this process.
Data collection stations that continually record data allow researchers to use technology to create cost-effective methods for gaining knowledge. The scientists at NOAA are planning for more sites in the Gulf of Mexico, throughout the Pacific, Saipan, and American Samoa. With each buoy And every tide gauge comes more insight and more potential for mitigating the damaging long-term impacts of global climate change.